What's going on, everyone? My name is Johnny Bandon, and I'm the CCNA instructor for your CCNA video series. And in this video, we're continuing with our wireless fundamentals, and now we're going to go over radio frequency. So this is such a fun topic to teach about, right? No sarcasm, really is. And like I was explaining in the intro, RF as a technology is something that people dedicate their whole careers to. Electric engineers that work with RF their whole lives. It can be very complex. Physics majors learn about RF. So what we're going to learn about is the basics, just to get you familiar with it. The different ranges in RF that you need to worry about, like Wi-Fi channels. And then specifically stuff that can happen to RF, just the basics, right? That you need to be aware of when deploying a wireless network. Stuff like interference, what a good signal strength is, stuff like that. Things that are important to you as a CCNA or a wireless engineer or someone that's deploying wireless onto an enterprise. So that being said, let's go ahead and get started. So again, the basics, what does RF stand for? It stands for radio frequency. And a radio frequency refers to the use of electromagnetic waves for wireless communication. And yes, waves. So you'll see what we mean by that in a second when we try to represent what RF is, or a sine wave, as we like to call it. We use a Y and X axis, and we say that each wave is a complete cycle. So essentially here, our complete cycle would be, let me see, change my pen color, would be where 2 points meet again on this axis. So right here and right here. That's one full wave, right? And that is considered a frequency, what I just drew on there. So it uses electromagnetic waves for wireless communication. So this is how we represent those waves. Then RF signal travels at the speed of light, can pass through most objects depending on the frequency. And this rule changes when you're talking about the changing of frequencies. And we're going to get into this as well. Pretty much the width of a wave, right? That's what a frequency is, and we're going to jump into it. And then the unit of measurement we use for RF is hertz. So whoever discovered that we can measure this electromagnetic waves and call it a frequency for like wireless communication, his name was Hertz. And so now that's expressed in hertz, megahertz, or gigahertz. Usually you won't see the terahertz. You will see kilohertz here. Essentially 1 hertz is 1 wave as in a second. So essentially what we have here on this chart, let's say this is 1 second. So we have 1 wave, that's 1 hertz. Okay, some more fundamentals. So the wavelength of an RF signal is inversely proportional to its frequency. And the frequency is going to determine how it propagates, or the characteristics. So what do we really mean by that? So again, if we draw our chart up here again, and let me just change the color for the actual sine wave here. Let's say we got something like that. And on our axis down here, let's say this is time. So this is 1 second in time. Well, how many cycles did we have there? So that means it took 1 second to do how many waves? How many full complete waves? So you can just go by the peaks here. Right? So we had 1, 2, 3. So that means in 1 second we had 3 hertz. So now that is a frequency, right? So the wavelength determines the frequency. So if we draw this again, and we do something like this. So in 1 second, how many waves did we get? A lot. The frequency of complete cycles increased, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now that's 10 hertz, right? So you see how we see the frequency, how it changes. And you notice that the more complete waves we get in a cycle, the smaller the width becomes. So what does that mean? So we're talking frequencies, and we're talking stronger or less strong frequencies or higher frequencies. The shorter the width of that full cycle, that full wave, the higher the frequency. So that means it's more like condensed almost, the more cycles we get in a second. So that means like HF here, we have, let's say, 4 megahertz. That means within a second, we have 4 million hertz, 4 cycles, 4 waves happening in a second. And then the size, the width of those wavelengths here, you see, would actually be 100 to 10 meters. And the smaller the size or the width, excuse me, that's important, the width of the wavelength, the higher the frequency goes. So you kind of see that relation. And then we can change, or RF signals, we call them analog as well, right? They're not digital, not ones and zeros, but they can be then further modulated, meaning that these RF signals can be changed in a way to actually carry information. So essentially we can have these waves represent ones and zeros here in its phase. So like right here, that's a 1, that's a 0, that's a 1, and that can actually represent information. And then understanding RF interference is going to be very important when deploying our wireless networks. So knowing where we sit as a Wi-Fi signal, 2.4 gigahertz, 5 gigahertz, by knowing how this signal, this frequency is modulated, the cycles in it, can help us determine whether or not it goes through interference worse or better, or what can interfere with it more, right? Because competing frequencies interfere with each other. And we're going to get into that. So let's go over frequency some more, right? What does frequency mean? So frequency refers to the amount or to the number of complete cycles of that electromagnetic wave per second. And that's going to be measured in hertz. So this wavelength, those are complete cycles, right? The wavelength, the smaller it gets, the more cycles you're going to have in a second. So this axis here is, let's say, 1 second. So here we have 4 hertz. So in wireless networks, frequency determines the speed at which data can be transmitted. So what do we mean by this? Well, the higher the frequency, meaning the more cycles per second, the more data transmission we can get. But there's a caveat to that. The stronger the frequency gets, the more power you need. And the more power you need, the more chance for attenuation we get on those higher frequencies. And that's why we need the higher power. Because if we go back to our chart, going over the signals, you notice this EHF. Well, if that's going to get us the most data transfer, if we're going to get the most transmission rate, the most bandwidth out of EHF, why not just always use it? There's a lot of reasons. Well, one, the wattage it takes to actually send EHF and to actually get it dialed in, right? To actually get it to receive properly on the other end is not as easy as, let's say, some of these other signals. So really, when it comes to Wi-Fi signals, we found the perfect range that'll work for in the house or in an office that allows us enough power that doesn't drain the actual power coming in, the DCs coming into our office, and it still allows that good signal propagation. So the frequency bands used for Wi-Fi networks are typically going to be 2.4 and 5 gigahertz and now 6 gigahertz. But we're going to go over 2.4 and 5. And within that range, so essentially we say the 2.4 gigahertz range. What actually we mean is that from 2.4 to 2.5 gigahertz, we're going to set channels. And what these channels are going to be is saying that, hey, if you're on channel 1, you're allowed to use these frequency ranges to send data back and forth, to send and receive. Because the Wi-Fi enabled device and the access point have to be on the same channel to communicate. They have to be on the same frequency. One transmit and one receive frequency within this channel. Well, you can see here that each channel gets its own 22 megahertz, give or take. So each channel has 22 megahertz of available data to be transferred. And then with 5 gigahertz, this raises. And I'll find a chart and we'll bring up a chart of the 5 gigahertz range actually. If it's not in the next slide, it's not. But essentially it has the same thing. In 5 gigahertz, there is channels. And I believe it's 80 megahertz or 40 megahertz that's available for you. Let's go ahead and take a look. 5 gigahertz channel with... Actually, yeah, so it goes in 40 megahertz. So the channel width is 40 megahertz, but we can increase it. And it kind of goes with like 2.4 megahertz and why it's more widely used because we do have more channels that we can use, right? And less power that it takes to use 2.4 gigahertz. When you start expanding that channel range, so let's say we go from like 22 megahertz in our channel, let's say we want to do 44. That opens us up to a lot of interference from other devices that could be within this huge bandwidth range or that channel range. Important thing to know for the CCNA is that 2.4 gigahertz, 5 gigahertz are going to be the frequency ranges we use. And a lot of this depends on like your governing body. So like in America, only channels 1, 6, and 11 can be used for commercial use. But I think in Europe, like channel 13 can be used, channel 14 can be used. So also these ranges are set by like our standards and regulations of the governing body we're in. And we're going to go over that in the next series of videos, but just something to be aware of. Okay, so now that we went over that, let's go ahead and go over amplitude. So if frequency is the width of those wavelengths, amplitude is the height. So we can also, on this axis, go over the height of the wavelength. And the more amplitude we have, the more data we're going to have, the better the signal is going to be. So amplitude is the strength or power of an RF signal, and that's going to be measured in decibels. So essentially what that means is, if our signal is really strong, it's clear, we're going to have these high wavelengths. That's going to allow us more throughput. But as we attenuate, meaning as that signal leaves our access point and goes to the far reaches of our offices, those wavelengths get weaker and weaker and weaker until it's flatlined, right? Back to the noise floor. And essentially, depending on where we sit, that's going to determine the strength of how well or how good we receive that RF. So that's the amplitude. So again, higher amplitude, that's more strength, more power. And then this wavelength distance right here, that's going over frequency, right? So to ensure reliable wireless communication, the amplitude of RF signal must be sufficient enough to overcome noise and interference. So what we mean by this, essentially what happens to that wave, and let me see if I can do some good drawing here. Let's say we have this wall right here. And then we have our user sitting here. And then we have that signal. We have that strong signal. Let's say it's 5 gigahertz. And this kind of goes into how 5 gigahertz is stronger, but since the wavelengths are more condensed, it's actually harder to get past obstacles and interference. And we'll go over that. But essentially what happens here when this hits here, all of a sudden the amplitude goes down because this wall is essentially blocking or interfering with that signal in some cases. So actually having that longer wavelength actually helps go through objects like that. Actually helps with interference, but you don't get the same data and throughput. So kind of like a yin and yang, give and take, right? All right, and then modulation. So modulation is a process of changing something on that signal, whether that be the amplitude, the frequency, or the phase of an RF signal to carry information. So modulation is how we take like our 2.4 gigahertz range and actually make it available to do 54 megabits of throughput. What we do is we can change the modulation, we can take it out of phase, and what that means is that essentially, typically we start here, right? Let's say this is at 0 degrees, and up top is 180, then we have minus 180. So actually, let me draw this a little bit different. So we got this axis here, right? And our wave is starting at 0, comes down like this. So this is starting at the 0 phase. This is one phase shift. Starting at 0, and then like each cycle, right, ends at 0. Okay. Now let's say we take that signal, and let's say instead we start a signal at the same time, but out of phase at, let's say, 90 degrees. So now we come like this, and I'm not a good drawer. But now, since we started that signal out of phase, now we're able to say, well, this could be a bit, this could be a bit, and now this could be a bit, and this could be a bit. So now we're getting into modulation of Wi-Fi, and this doubles. So what I mean by that is there's like 8 phase shift keying, there's 16 phase shift keying, and then it keeps doubling until now we have something called 256 QAM on our Wi-Fi 6 networks, and that allows us to send these signals all at the same time, all in the same frequency range, just out of phase from each other, but all lining up and synchronizing to actually give throughput on all those out of phase frequency ranges. And when I say out of phase, I don't mean out of phase because that would indicate that it's not a proper signal that you can receive, starting at different phases as the sine wave, right? And that's going to allow us to get more data. So really this term modulation, as far as for the CCNA exam goes, right, I don't want to get too deep into this. They offer varying levels of data transfer rates and resistance to noise and interference. Now, I've been telling you this whole time, my day job was satellite communications. So like anytime we were configuring a modem that would determine how we sent our SHF signals up to the geosynchronous satellite, I don't know, I think it was like 32,000 kilometers up in the sky, something like that, 35,000. We would add phase shift keying. And if we went up to 8 PSK, we needed a lot of power to be able to take that frequency pretty much out of its different phases and start them in different phases. And then because of that, we became more susceptible to interference. So then we'd have to do something called forward error correcting on the bits that we would lose out of all these phases. So it's kind of like, again, a yin and yang, right? If you want to add more modulation to give you more data rates, more bits can happen on that sine wave through its cycles, then you're going to have to add more power. You're going to have to optimize that signal. Okay, so without making this video like 2 hours long going over RF, now let's go over some interference. So path loss. This is going to be the reduction in signal strength that occurs naturally. So essentially that means we put an access point in an empty room, and this room, let's say, is 1,500 square feet, big room. And from end to end, we can see how its RSSI gets weaker at the wall. And then towards the middle of the room, the RSSI gets stronger. So why did it lose? Why did it attenuate and get weaker? It just naturally happens through distance, through air, and path loss can include the obstacles and other interference, like other signals interfering with it. But path loss is just a good way to describe, like, hey, from my access point all the way to office B, we have this path loss interference. And then reflection. So reflection is a phenomenon where a wireless signal gets sent, it hits a roadblock, and then bounces out, but then continues its journey, right? Propagating out. And then this computer, let's say it tries to connect to both these signals, and then it becomes out of phase. So not the phase shift keying we were talking about earlier, actually comes out of phase. It won't be able to actually receive that signal and make communication. So reflection is something we have to worry about. In today's modern networks, typically with the 2.4 and 5 gigahertz ranges, when you're going through a lot of obstacles, you go with the 2.4 gigahertz because those longer wavelengths go through objects better. And if you're closer to the wireless access point, you want 5 gigahertz. But this path loss or this reflection, something you got to think about for signal strength with this out of phase phenomenon, out of phase, that happens where now this computer can't connect, isn't really all that common. Just something we have to talk about, right? And then noise. So what is noise? So if we look at Insider here, what noise is all these other signals or frequencies riding on your same channels and interfering with your strength. Because essentially what we have happening here is we have all these other ones sitting on top. And let's say this is our noise floor here. Now we have these other signals riding on top of ours. So we're not able to get that full channel. So that's the interference we're getting. Now it's okay because we authenticate. So it's actually really not truly interfering that much, these weaker signals that you see down here. But if it does get too crowded, if it does get too much where we're actually sending maybe our sister ID, SSID from the same access point on that same channel, we might get some interference, right? If we have 3 different autonomous access points all broadcasting on this channel, all with the same SSID, but it's different signals, right? Not a part of that same seamless system, we're going to get interference. And you see right here, this signal strength here. So essentially, we can actually see as well what our signal strength is. And the closer to 0 we get, the stronger our signal strength is. So this right here is going to be our RSSI. That's our receive signal strength indicator. So receive signal strength indicator. So this application Insider is just this graphical representation of what our Wi-Fi NIC is actually seeing. It's saying, okay, I'm only getting minus 45 decibels. So that's my best signal. So that's what I'm going to want to connect to. And then here we have the 2.4 gigahertz, 5 gigahertz range. You can see how less crowded the 5 gigahertz range is. I mean, it still is, we still have things riding on top of each other, but you can see, and in my office, I wish I could show you my access point where it sits, but it's right here in my office. So that's why you see these signals right here so peaked. I mean, my computer is literally like a foot away with no interference. Usually you don't see that good of peaks on 5 gigahertz if you're in another room or it has to pass through walls or any obstacles. Okay, so that's going to be it for this lecture. I don't think I want to jump into power right now in this lecture. It's going to be way too long of a video. So I want to thank you all for viewing and stay tuned for our next video. And if you are interested in any live virtual training, in-person boot camps, or you want to get your team or your unit or your organization certified, please hit that link below and learn how Trepa Technologies can either come to your work or train you virtually. Thank you.